Good afternoon. Welcome to course Thermodynamics of Materials. Today we are into lecture 167 and 168. We are considering the Gibbs Phase Rule and taking several examples to illustrate the Gibbs Phase Rule. That means to find out the degrees of freedom and to show how by applying these degrees of freedom we can define the state of the system at equilibrium, giving the temperature, pressure and composition of the coexisting phases. So we actually completed three examples so far last class. Today actually we will take up next problem, namely problem 4, and problem 3 is over. 3 is over. One thing actually this was the stability diagram or equilibrium diagram for the system CO, that is in the form of carbon dioxide plus carbon goes to 2CO. This I discussed at length. Only thing I want to add one point here in the last class, that is, concentrate on this domain, this hatch part, this is, I wrote, unstable gas. This gas cannot be realized, cannot be attained ever, because anytime you actually at any temperature you may have certain gas composition. Certain gas is, suppose this is the composition at any temperature, then this will drop to this equilibrium curve, carbon saturated curve. This is the carbon saturated curve. This I said. This is unstable. I said it is shooting. So this reaction actually this CO will dissociate back into carbon dioxide plus carbon, because CO is made higher than this, so it will move to the left, producing carbon. So shooting will occur, and this situation is activity of carbon greater than 1. So what I want to add today, that follow this curve ABC, I said carbon saturated curve, written here ABC for P is 1 atmosphere. Don't consider this one. This is for 10 atmosphere. Just one diagram is enough. If I can explain with one diagram, with one pressure, for other pressure the same arguments. So what I say, this is a carbon saturated curve. It is written here, carbon saturated CO2 gas. This is there, and this one. And then below this, what I wrote, below this is CO2 carbon unsaturated, means activity of carbon less than 1. And yes, I am back to this carbon saturated. What is the activity of carbon is 1. And what I have written here, activity of carbon greater than 1. This is unstable gas, unrealizable gas. So, and actually shooting occurs, shooting zone image. This activity of carbon greater than 1, add this term that it is a supersaturated. Carbon supersaturated. This is carbon saturated, this is carbon unsaturated, this is carbon supersaturated. So just since there is no space to write here, okay, but you can add here carbon supersaturated. Okay, so shall I so here carbon supersaturated, shall I write here, I'm writing here carbon supersaturated. This point was missed. So again I am showing here. So in case, by the way, don't see, this is figure 6B, 6C, 6B. figure 6b, 60, 60, don't look at them now. This is example 6. And this figure is for figure 5b, for example 5. We'll take up example 4. So these are actually far away. So don't consider these figures, so concentrate here, okay? I am redrawing this, the simple sketch. With the simple sketch I am showing you. This may help you. This is the percentage CO versus this. I am redrawing as it simplified form. What is this? 1 atmosphere curve I am drawing. So this is 0 to 100. CO in CO2 mixtures. Just for clarification, in CO2 mixture, okay? In CO2, okay? Mixture. You may add this. Temperature is okay, very good. This is say 1273 typically, and here is 100%. So it comes down like this. Like this. Okay? This will curve this. This is okay. So this is what? This you say, this you see. I say, this is this first. This is this. Forget about these other lines. Okay, okay. That's one. This is for 1 atmosphere. Carbon saturated. Carbon saturated CO2 mixture. Carbon saturated. This is given by this equilibrium curve. So this is for 1 atmosphere curve. P is 1 atmosphere. So total pressure is 1 atmosphere. This is drawn. This curve I am drawing, ABC. So you want to repeat this A, so B, okay, A, maybe here I can write B, okay, C, ABC, ABC curve. Now what I want is this carbon saturated CO2 gas, CO2 mixture, carbon saturated CO2 gas mixture, CO2 mixture, CO2 mixture. Oh, sorry, actually I am overlapping with this. This is carbon saturated CO2 gas. Okay, and this is what? This zone is what? This zone. This is also a stable gas. This is stable. This is stable. Both stable. Carbon unsaturated. Right here in bracket, activity of carbon is 1. CO2 activity of carbon is 1. And this is what? This zone. This is the curve. Along the curve, carbon saturated. And this is the diagram for this equation, for this reaction. The representation of this reaction with the curve. For this answer is this curve, ABC curve. This ends. How do you represent this equilibrium? By this curve ABC. This is the answer. For what pressure? 1 atmosphere as a function of temperature. This is 673 Kelvin. This is 270 roughly, okay. And this may be 50 here. You have 50, and this is correspondingly. This is roughly 50. It is 50 here. 50. This is actually, you don't see this. This is 670. This is 675 degrees centigrade, and 273 is 948. This is roughly 948. 948. T, Kelvin. These are 675 degrees centigrade. This is 50%. Okay, this is 50%. Okay. This is 50. This is percentage CO plotted against temperature. So this is carbon saturated activity of carbon, and this is what below. I am showing this. This is I am showing to the right of this curve or below this curve. Means this zone is carbon unsaturated. CO2. You don't have to write gas, it is implied. Carbon unsaturated, CO2, activity of carbon is 1. It is CO2. What is the activity? Activity of carbon is less than 1. Unsaturated. And this one is what? This is actually, this has many, this is to the right and or below. Means this zone. Right below the curve. To the right of the curve. To the right. And or below the curve or to the right of the curve, and to the left or say you can say if I actually give this to the left below or to the right or to the left, okay, below this curve, the left to the right is, this is what, this to the right I am writing, this is carbon supersaturated. This is also supersaturated. The space here. No, this actually, it is better it is better to the right, it is better I consider to the right, it is better. Activity of carbon. Okay, these are all actually mixed. Carbon saturated CO2, repeat. Activity of carbon is what? 1. This is along the curve, and this is where carbon unsaturated below this or to the right. So this part, okay, and this part, okay, you don't have to give this, okay, to the right. I'm showing to the right, and this is to the left. Carbon super saturated. Supersaturated. What is the implication of this? Carbon saturated CO2. What is the activity of carbon? Greater than 1. So what happens? This is unstable gas. Space there. Unstable, I have written here. Unstable gas. I'm just copying activity of carbon greater than 1. So only I added carbon supersaturated. Unstable gas. Or also I wrote here shooting. This is a shooting zone. Shooting means carbon deposition. Shooting occurs, okay. Which one? This left means, just keep this. This is actually shooting zone. Just show this way. This is kind of, this is ABC. Name of this curve is ABC. 948, okay. 673. ABC curve. So I repeat this. What I wrote this. ABC curve is this representation of this equilibrium. CO equilibrium or this reaction. CO2 plus C is 2CO. What is the activity? This carbon solid is in equilibrium, carbon solid is present, so activity of carbon is 1. No surface. So this curve, but beyond this curve, to the right or to the left, or you may call it below or okay, below this. Oh, both ways actually it is. I made a mistake actually there. This may be possible. Oh, okay. And on this curve, it will be this curve actually. This okay. Okay. Oh, yes. This is also possible. This is actually right way. So to the right of this curve or below the curve, what is the situation? Carbon unsaturated CO2. This is realizable. This is practical. This is okay. Very much okay. Equilibrium state. Equilibrium. It can be kept. It is a stable gas. It is in equilibrium. The CO2 gas itself, a mixture. This gas mixture is possible. And of course, not only the percentage, but also temperature. This temperature and certain percentage and this temperature. The temperature greater than this. Or if you have a temperature, percentage CO is below this. Anyhow, means this zone, carbon unsaturated, activity of carbon less than 1. So 3 situations, repeat, activity of carbon is 1, saturated, carbon saturated, given by the curve ABC, and carbon unsaturated CO2, this is realizable, this we can have, hold it. Activity of carbon less than 1, this is given by this side or below means this zone, to the right or below, and this is to the left or above. This is carbon supersaturated. Activity of carbon of greater than 1. This is unstable gas, and shooting will occur means this will deposit carbon, and reaction will move to the left, so that you suppose you maintain a gas here, keep a gas here. This is an unstable zone, so it will say at a certain temperature, then this will drop. That's keeping the temperature at that temperature fixed, drop to this curve, as I showed other day, that B double prime to B, B double prime to B. It falls B to B, B double prime to B at that temperature. So this will fall onto this carbon saturated curve situation, carbon saturated condition. So it is producing carbon, and so it is it will return to this curve. Because this is actually, this zone is actually, as I said, unstable zone, but this is stable. This is carbon unsaturated is stable. So 3 cases, activity of carbon is 1 along the curve, activity of carbon less than 1, okay, to the right or below the curve, and activity of carbon greater than 1 to the left or above the curve. This is carbon supersaturated, means unstable gas. This gas cannot be realized, cannot be created, cannot be produced. Anytime you produce this, we try to artificially make this curve, this composition here, then it will soon actually move this direction, and so that it will fall onto this curve. Giving the temperature, it will fall onto this. Or suppose you have actually increased, the other day I was discussing that you have actually what you have done, you have actually giving the temperature, you have actually decreased for giving composition. If you have decreased, we don't change the percentage CO, but decrease the temperature from this. Decrease the temperature, you land into this zone. Then also it is a supersaturated situation, and then it will actually giving this temperature. You have a you have decreased the temperature. Suppose you have decreased the temperature to here. Here it is keeping this composition, it is carbon saturated and it is stable. This is stable, this is stable. So carbon saturated is stable, but you have decreased the temperature, keeping the percentage CO constant this way, because then it will fall. Suppose you have come here, then it will fall like that. Repeat. It is or it is better I may show with this tip of this arrow. Suppose you have kept here, this is unstable. So what it will do, what you have done, keeping this at this temperature, you have actually at this composition, then you have decreased, arrow means decrease the temperature, then you have come here, then it is unstable, supersaturated. So what it will do at this temperature come down straight, will fall onto this curve. This composition will be realized. This will be this carbon saturated gas composition will be obtained. This is the story. So the term only this discussion I did, actually it is carbon supersaturated condition here. So it makes sense now. This actually you have a nice situation, a nice comparison. This is activity of carbon is 1, carbon saturated. This zone is carbon unsaturated, activity of carbon less than 1. This zone is carbon supersaturated, activity of carbon greater than 1. This is realizable, and this is very much simple carbon saturated gas. This equilibrium actually this situation, and this is actually here it is carbon unsaturated, and this is also realizable, but this gas actually is not realizable. It will start depositing carbon and will fall onto this curve. Okay, giving the temperature, say giving if it is temperature is given, then fall onto the curve at the given temperature. Okay, suppose it is the temperature you have this, then this temperature. Suppose you are here at this temperature, you are here, it falls onto this. Or say you are giving composition. You are here. Suppose you have what you have done. Suppose you are here equilibrium. You have increased CO percentage. Then it is unstable. It will fall to this. Or alternatively, given composition, you have decreased the temperature. Again, what you will do? So suppose here this is the temperature. The corresponding point is this. This will fall to this. By moving in the reverse direction. That is the 2CO going to CO2 plus. So this I discussed last year, but actually I wanted to continue for a while. So I am removing this. Today I will take up problem, means example 4. Okay. So this figure can be out. This figure is not required. So I am removing this. Sorry. Sorry. So now it is 4. Example 4. So what I will do? So this I will remove also. This is not required. Mapo? Alright. দেখো ভাই হাতটা একটু নড়ে গেল মনে হলো, একটু ঠিক আছে না? ঠিক হ্যাঁ, পারফেক্ট আছে তো? একটু নড়ে গেছিল একটু মুছতে গিয়ে। It's okay? It's okay?
স্লাইটলি মেটেরিয়ালসটা স্লাইটলি কেটে গেছে।
না, সেটা
আগে থেকে ছিল।
Thermodynamics is okay.
হ্যাঁ, thermodynamics is okay.
That's fine. Actually, when I was actually, this.
Be careful.
This. Removing this slightly slit. It's okay.
No issue.
It's okay. Thank you so much. So let us remove this. Bapu, hello. কারো কথা দেখেন আবার নড়ে গেল একটু।
ঠিক, হ্যাঁ ঠিক আছে।
Fine. Let us, okay. So today's class actually begins now, in a sense, okay. This was removed, all removed. So don't look at these figures, okay. These figures. This is for 5, example 5, and these 2 and this one, these 3 for figure 6b, 6c, 60 for example 6. So start this one. This is what I'll consider this carbon solid. It's like 3 CO2, CO, and I am adding oxygen, okay. CO gas, CO2 gas, and oxygen. This is the system. Very interesting now. This is make a phase rule analysis of this system. See, note that I am not giving the reaction this time. This is the first time that I am not giving the reaction. Instead, I am giving you the system, reaction system. But you find out the reactions yourself. Okay. So, what is this? So, if I may draw this again, pressure P, temperature T. What you have here? Carbon solid, and you have CO, CO2, and O2, gas phase. This is your is better. CO, CO2, O2, okay, the gas phase. Gas phase. So make the phase rule analysis. How will apply? This is equilibrium. Figure. This is only one figure, so it is figure 4 actually. Figure 4. Okay. Only one. So start. The Gibbs phase rule is what? F is C minus P plus 2. What you have to do? Make a phase rule analysis of this system at equilibrium. So C, find out C is what? So in a different way we will find out C is what? Number of elements. So you see here you have to find out the reactions, independent reaction equilibrium. Number of elements, what are there? Is 2 elements. So what the CO is what? You know, see how I am actually finding out the number of independent reactions. Follow this. Is what? Number of species minus number of independent reaction equilibrium. Okay. Since it is 2, number of species is how many? We see 1, 2, 3, 4. 4. You can write them. Who are there? C, CO, CO2, O2. 4 species. So what you get out of this? Number of independent reaction equilibrium. Reaction equilibrium is how many? Is what? Is 2 and now is nothing but 4 minus 2. 4 minus 2 is 2. Which are they? Which are they? You can say, write yourself now. Reaction you have to write yourself now. Okay, since it is not given, it is just said, and they are freely reacting. Freely reacting, so all possible reactions are available. So we write, okay, the independent, some, you choose some independent one. So suppose I am writing this, C solid plus half O2 gas is CO, is one equilibrium. C, anything with anything else. Anything with anything else will make a reaction equilibrium. Okay. So anything with anything else, of course, that should be stoichiometrically sound, should be correct. So CCO2, this is a well-known reaction also, called reaction 1. Independent reaction equilibrium I am writing. And which are, these are, which are these below. Okay, which are 1. Second is what? C solid plus O2 gas is CO2. Right here, this is also gas. This is also gas. This is equation number 1, reaction 1. This is CO2 gas. Reaction 2. Reaction 2. So these two independent, but note here, you have to note actually. Note here some important concept. Note here, I am telling you before I write. CO plus half O2 goes to CO2. Can be a reaction, independent reaction. CO2 plus C is 2CO. Another possibility. So why not there? So we are writing, then there are 4. So out of these 4, 2 is independent and 2 dependent. When you consider these 2 independent, the remaining ones are, these 2 independent, remaining ones are all dependent. How? Because if you eliminate oxygen, you get what? CO2 plus C is 2CO. If you eliminate carbon, then you get what? CO plus half O2 is CO2. That means these 2, the subsequent 2 are manufactured from this. Well, this is one lesson. That oil, sir, I have 2 independent. See, this 1 and 2 are mutually independent. These are mutually independent, but you can manufacture. Good. But still another thing. It is not, there is no compulsion that these must be the independent, these 2 should be the independent reaction equilibrium. This should be only. No. Remember, number is more important than who is there. Here also, like degrees of freedom, number is more important than which are the chosen, which are the variables that freely used. Which are the variables used as the degrees of freedom. Which variable? That is secondary. Number is the cardinal point. That is the central thing. That is the main thing, chief. So here also, number is how many? Independent is 2. 2 is important. Which 2 is not so important, okay? Is not, is secondary. So you have chosen these 2. So what I said, so for example, CO plus half O2 is CO2 and CO2 plus C is 2CO. You can consider these 2 that I have not written yet, these 2 as independent. Then in that case, suppose there are 3 and 4. 1, 2, 3, 4. 3, 4 independent, then 1, 2 will be dependent. There is no hard and fast rule that these reactions should be independent. So, choice. It's a matter of choice. No problem, absolutely no problem. No problem. So, note here that this, so not only that, 1, 2, 3, 4. So, 1, 3 can also be. This 1 and say CO plus half O2 is CO2. Not this. CO plus half O2 is CO2 is another. These two are independent reactions. Possible, no problem. So remember, two number matters. Which there is secondary. Note here. CO gas plus half O2 is CO2 gas. This is a possibility. How you get this? Obtained by elimination of carbon. Right? This is how you obtain. Obtained by elimination of carbon. That you can do yourself. Call this equation 3. Fourth is elimination of oxygen. What you get? CO plus, this is also very popular reactions. Oh, sorry. CO2 gas plus carbon solid is 2CO gas. This is 4. This is 4. Obtained by elimination of oxygen. These are so manipulation constructed out of this. So 1, 2, 3, 4. I am giving you any two will do as independent reaction equilibrium. It can be 1, 2. It can be 3, 4. It can be 1, 3. It can be 1, 4. It can be 2, 3, etc. So let us write down few lines. So note here this one. Okay, obtained by when 1 and 2. Write this. When 1 and 2 are treated as the two independent give a fencing here. This will help. Give a fencing here. This is okay. Will protect it. As the two independent reaction equilibria, 3 and 4 can be included in the independent reaction list. They cannot be independent. 3 and 4 cannot be. When 1 and 2 are independent, this is okay. So conversely, when 3 and 4 are treated as the two independent Independent and short independent. Independent reaction equilibrium. I'm writing equilibrium short. As two independent reaction equilibrium, you understand the independent reaction equilibrium. Okay, that is 1 and 2. Okay, 1 and 2 can be included in the independent reaction list. In the independent reaction list. Not only this, it is not that these two or that two, any two. So this actually which two of these four reactions, reactions are independent reaction equilibrium is which two is flexible and is a matter of choice. Is a matter of choice. So it is also quite possible. Give fencing here also. Yeah, so it is also quite possible to consider 1 and 3 or 2 and 4 or 1 and 4 or 3 and or say 1 and 3, 2 and 4 or 2 and 3 or 1 and 4, etc. etc. I am giving you actually, etc. One and 4, etc. as to independent reaction equilibrium. I am writing now independent reaction equilibrium. So this concept will be very useful. Don't confuse. I will consider 1 and 2. I will work with 1 and 2, but it can be otherwise. Careful. Given this this understanding, given this concept, then we move on to write this here. So P is how many? Note here. So we are actually here working. C is here. P is what? P is number of phases. So this is bracket. This bracket is the note here. Bracket close. Note here. Bracket closed. So no number of phases. How many it is? See, 1 solid, 1 gas. 2, 1 solid. What is this? Carbon. 1 gas. 2 phases. So Cp. So use here. C is 2. Phase is 2 plus 2. This gives you 2 degrees of freedom. So typically we consider temperature, pressure. Pressure means total pressure. So this pressure. Okay. So demonstration. Now you have to demonstrate. It is finding the degrees of freedom. Then you have to demonstrate how by fixing a number of variables state of the system can be fully defined in terms of temperature, pressure and chemical composition of each phase at equilibrium. Repeatedly I am saying this. So demonstration. What? Suppose T, fixing T fixes what? What it fixes? Suppose 1 and 2 I am considering. Fixing T fixes KT1. KT1. So KT1 is what? Write this. 1 is PLDC, PCO over activity of carbon, PO2 power half. Okay. Call this equation 5. Again, fixing T. Since you have two reactions, you apply this fixing T. So T is, for example, 800 Kelvin. So, and equilibrium constant is a function of temperature from delta G0 you will get. This you know. Fixes what? The second one also, KT2 now, is what? Is PCO2 by activity of carbon, PO2. See, right, activity of carbon is how much? 1 pure. Here also 1. So call this equation 6. Those you see two unknown, which are the three unknown. PCO, PCO2, PO2. Two equations so far. Third equation is what? Third equation you see also fixing P. This leads to P is what? P is known is PCO plus PCO2 plus PO2. Three gases together. Okay. This gives you another equation in the form of 7. So 5, 6, 7. So solving equations 5, 6 and 7. 3 equations, 3 unknown, right? Yeah. Right. This is a 3 equations. So 3 unknowns. Solving 3 equations, 3 unknowns. Who are there? PCO, PCO2 and PO2 can be found out. Suppose PCO is known. This leads to what? XCO, mole fraction, composition. Okay, mole fraction is what? PCO over total pressure. So this is known. Similarly, PCO2. This leads to XCO2. This PCO2 over P is known. Okay, PO2 is known. Hence XO2 is PO2 as PO2 over P divided by P is also known. Okay, all are known. And this is the composition of the gas, mole fraction or mole percent, whatever. What else? Solid one. Another phase is solid. Carbon solid, pure. So its mole fraction is pure. So full system is defined. So thus by fixing the F, which is nothing but 2, which is equal to 2 F variables, by fixing F variables. F is the degrees of freedom. The system is fully defined in terms of temperature, pressure, and composition of each phase at equilibrium. So this concludes example 4. Example 4 is over. Okay. So there is no actually stability diagram. Actually, it is actually not big deal. The one that I have already considered is problem 3. That is the main thing. And the other stability diagrams I will show you. Okay. Now next is 5. 5. What I am trying to change this? Oh, sorry. What change I made here? What change I made from example 3? It was CO2 CCO. What I did here in this example 4, what I did? Added oxygen. So this is a lesson. If you add oxygen may be present also. So why not include that species? So I have added oxygen. Then you found that the phase rule analysis can be satisfactorily made. There is no trouble. Okay. Degrees of freedom, everything is very simple and can be accomplished, no problem. Okay, and we have demonstrated satisfactorily how this with the use of F variables, with the use of F degrees of freedom, we can define the system at equilibrium. So now we keep changing. This is fifth example. Here what I am doing, see, we are returning FeFeO. Okay, FeFeO have we considered? Yes, we have considered. Second problem, FeFeO CO2. Follow FeFeO CO2. What we are doing here, FeFeO CO2 and carbon. We are adding carbon. So this will be a complicated, little bit more complicated, and we will solve the problem. Okay. So FeFeO. Okay. This is the FeFeO solid. FeO solid, carbon solid. These solids, and CO gas and CO2 gas. This is a system. Again, I am not giving you the reaction. It is for you to find out the independent reactions. How many there and what they can be chosen as. That is a matter of choice. But so this is actually, remember, example, I repeat you, example, what is this called? Example 2 was this. Suppress carbon, FeFeO CO2. But see, introduce carbon, another solid, see how it will be, how modify the degrees of freedom and the system, etc., and how you will define the state of the system at equilibrium by independently choosing F number of variables. So this is to be. So I am removing this. This is not needed anymore. Oh, sorry. This is our system. New system. Okay. New example. Application of the degrees of freedom. So start here. Again, give a sketch. On the left hand side, not bad. Give a sketch. This is the pressure as before. This is the temperature. What you have written, what you have got? AP solid, AP solid, FeO solid, and carbon solid. Okay, and what is the gas? Contains CO2 gas. This is in equilibrium state. Figure 5a. See 5b I will explain later. 5b subsequently coming. Okay. So remove this. Start. Let us see. I'm giving you okay, very good. This is fine. F is write nicely C minus P plus 2. C is what? Again apply. C is what? Number of elements. Go by the elements. Because you can go by independent reaction, you can guess. But it is better you go by this definition of C, number of element, with the definition based on number of elements, go by this, and using that information you find out the number of independent reaction equilibrium, and then you actually okay, using your choice write the independent reaction equilibrium. Okay, so first find out the number of independent reaction equilibrium, and to find that you find number of elements, number of components, number of elements. There is no stoichiometric restriction in those cases, so that's why I am not mentioning. So number of elements directly. What is this? Is what? Yeah, 3. I can write 3 easily. What are there? Fe, carbon, oxygen. 3 elements. 3 is what? We will continue this. Is what? Number of species. Species minus number of independent reaction equilibrium. Independent reaction equilibria is what? Number of species. How many? You write here. What are there? What are this? Number of species is what? How many? Number of species? 1, 2, 3, 4, 5. 5 species. 1, 2, 3, 4, 5. Write this. We are the Fe, FeO, C, CO, CO2. 5 species. Or what you are getting from this? Or number of independent reaction equilibria. How many? Is tell me, is what? 5 minus, is 5 minus 3 is 2. So you have 2 independent reaction equilibrium. Which are the possibility? Choice, your choice. Okay. So I am choosing actually which are here is 2. Okay, very good. So these 2 numbering. What I am writing? FeO solid. Or write this side, Write this side. Now remove this. So yes, so 2 reactions is one is FeO plus CO goes to Fe plus CO2, possible. The one already we consider. Another is maybe CO2 plus C is to CO. So these 2 we can consider. Okay, so no problem. There is actually how
1
many?
hour gone.
Start. What is the reaction which are chosen as which are chosen as, right? It is better I write this, which are chosen as what I'm writing, APO solid plus CO gas goes to Fe solid plus CO2 gas. You may call this reaction 1. Equilibrium 1, reaction 1. Another is CO2 gas plus carbon solid is what? 2CO. 2CO gas. Call it reaction 2. So this is okay. Very good. You might say, sir, what is the other possibility? Yes, other possibility is what? APO plus C is AP plus CO. No, 2 only. APO plus C. I'm writing here. APO plus C is AP plus CO. You could consider. If you consider these as independent, no problem. So these and any one of these two, like this. Okay. So very good, very good. So 2 independent reactions. So unnecessary will not actually enter into complications. Okay. So start 1, 2. You have got this very okay. Okay. So now P, C is okay. C already there, and number of independent reactions are already found. P is what? Number of phases. How many there? Tell me. Solids, 3 solids and 1 gas, 4. 3 solids, and name them: Fe, APO, carbon, and 1 gas phase. All gases are miscible, make 1 phase, 4. So 4 phases. Now you apply here APC minus P plus 2. C is already found to be 3. 3 minus 4. 3 minus 4 plus 2, 1 degree of freedom. So previously, in absence of carbon, how many it was? In absence of carbon, Ap, APO, CO, CO2, 2. It was 2. Because C was same, APCO. P number of phases was not 4 but 3. Ap, APO, and gas CO, CO2. So degrees of freedom was 2. So reduced to 1. And I will consider okay, further complication. Then I will get further reduce. F is 1 to F is 0, which is invariant. So next, that is next example. Example 6. So for the time being 1, what I choose? Conveniently temperature, no problem. So temperature. So what you get from this? Fixing. Now start here. Fixing T. It is demonstration. Up to this point, degrees of freedom is found. Now demonstrate. When you start demonstrating, that you fix the variable, temperature or pressure or partial pressure or mole fraction or whatever. Fix this and then demonstration, complete the demonstration. Demonstration of this. Thus giving the number of, giving the degrees of freedom is not enough. You have to show how it works, how it helps to define the state of the system at equilibrium. Fixing T leads to what? You know, this equilibrium constant KT, KT1, okay, fixing the is KT1 or just K1, it is not variable, I fixed it. KT1, shall I write KT1? Let me check. This is KT1, yes, it is better. KT1, not bad. KT1 is okay, sorry. Is okay. Is for the first one, right? Activity of Fe, PCO2, PCO2, and below denominator activity of FeO, PCO. Oh, you can always write this. I forget sometimes. Equilibrium. This refers to equilibrium, and these activities of solids are pure substances, and the standard state. So one. So it gives you. You can get it. This PCO2 by PCO equilibrium. So PCO2 by PCO equilibrium KT1. Okay. Call it equation number what? 3. Fixing T, same T. Since there are two reactions available, gives you what? KT2 is what it is? PCO square by PCO2. Activity of carbon is 1, okay? A plus BT, okay, wait a bit. It's okay. Okay. Very good. So where it is? It is 1. Okay. PCO square. What is this value? Activity of carbon is 1 pure. So this is again at equilibrium. You can write. So this is your 4th. So again, so solving equations 3 and 4. 2 equations, 2 unknown. Okay. What are the unknowns involved? PCO and PCO2. 2 equations, 2 unknowns, PCO and PCO2 can be found. So as it found, PCO is found. Oh, wait a bit, can found. Once found, then P is what? P total pressure is what? Total pressure actually no, we don't know yet. We don't know yet what is the total pressure. Is what? PCO plus PCO2. See, both are found. Okay. Okay. Total pressure found. Now, since PCO, now composition, go to composition. PCO is itself a composition, but if you want to express in terms of directly XCO, mole fraction, that is possible. PCO is known, that leads to what? XCO is PCO over pressure, total pressure, nothing else. Okay. This is mole fraction, and mole percent is mole fraction times 100. So this is also known. 1. PCO2 is known, that leads to XCO2 is PCO2 over total pressure is known. Okay, so this XCO2 composition of the gas phase is known. What is this? Total pressure is known, temperature is known. Solids, okay. AP solid pure. No, sorry about solids. AP solid pure. What does it mean? XAP is 1. Okay. Okay. XAP is 1. APO solid is pure. APO solid is pure APO solid. So XAPO is 1. And carbon solid is also pure, so X carbon is 1. So Thus, by fixing f variables is what? How many? One is one f variable. A variable this system is fully, the state of the system, you are right, necessary state of the system, it is at a state, the state of the system is fully defined what in terms of temperature, pressure and composition of each phase at equilibrium. Okay, so this is the demonstration over about the stability diagram. I actually ask you, I ask you to note this. This is the figure 5b. See, follow this. This is the stability. So this is the next section is stability diagram. Figure 5b. Okay. Figure 5b. Explanation. See, explanation. Put a bit as I'll be with you soon. Yes. Okay, I'm giving the explanation. Okay. Let us see. Explanation is what? I'm sorry. See, this is the stability diagram. Figure 5b. See these curves. This is already one is this curve. This is FPFO equilibrium. This one is already you have done in example 2. Now which equation? This equation 1 is represented by this curve FPFO equilibrium. Means what does it mean? What does it mean? Along this curve both coexist, FPFO. Both are in equilibrium, both are stable. FPFO coexist. Above it, as percentage CO increases above it, one phase will be eliminated. So Fe will remain, okay, and Fe will actually survive actually. Then it will survive, and this is the Fe solid will be stable. And below, when CO percentage falls below this equilibrium value, then FeO solid will be stable. So above one, below another. So Fe above, FeO below. This is discussed. So that's why I am not showing how the equations was developed and then it was plotted. So very good. Likewise, this is also plotted. So any one of them consider. This is CO2 plus C is 2CO means equation 2. I have written equilibrium 2. This is equilibrium 1 and this, and this curve is equilibrium 2. So this is also discussed in the last example 3 actually. Example 3 we discussed this, okay? Example 3. Example 4 is what? Example, right. Example 3. Example 3 we discussed at length actually. So this curve. And now this curve can be drawn for different pressures. What are the pressures I have chosen here? Okay. Okay, no, pressures. Oh, I have not written here. I should have written there. Oh, sorry. P is 0.5. Oh, this is very bad. I should have written here. So these are drawn for different pressures. This is for, let me write here. This is for the first one. P is 0.5. atmosphere. Second one is 1 atmosphere. Third one is 5 atmosphere. And the last one is 10 atmosphere. Sorry that I didn't mention, but I am not mentioning it. So this should be a function of pressure. So pressure should be specified. I have specified the 4 curves you see. This is actually, it can be 40 curves. Just I have, for example, I have drawn 4 curves. This is representing which equilibrium? CO2 plus C is 2CO. Carbon saturation. Okay. Carbon saturated CO2 gas means then that curve will represent this equilibrium 2. I have written here equilibrium 2. So what is the equilibrium state? Obviously you can guess, since, see, you have to show here how 1 degrees of freedom work. Follow, this is the temperature scale. I have a number of temperatures are chosen freely. So start with that. You have degrees of freedom is what? Your degree of freedom temperature. So what this? This is a temperature scale. Runs from 673 Kelvin to 1273 Kelvin. Just actually the range chosen, and this is the percentage here on the y-axis. So choose T1, T2, T3, T3, T4, and so on. So choose one temperature. Set T1. Set T1. Then T1. Then T1 temperature go up, and where it intersects, which at this temperature, at this temperature at which point, at this temperature, which curve rather, which curve intersects this FAPO curve, out of this 4 say, out of this 4, which one? So go up there, this curve, this is 0.5 atmosphere curve, 0.5 atmosphere total pressure curve, CO2 CCO curve, CO2 CCO curve intersects, actually this curve and this curve intersects at this temperature T1. So if you go up there, that means if you fix T1, so you start T1 means arbitrarily you are choosing. Then you have no choice over, then what pressure it must be? It must be where it is actually this curve, this CO2 CCO curve and this FAPO curve are intersect. Which curves? Of these 4, which one? Now must be this curve. And what pressure it corresponds to? 0.5 atmosphere. That means fixed temperature, pressure is automatically fixed at 0.5 atmosphere total pressure. So this is how you are showing 1 degree of freedom. Similarly, more importantly, T2. You will choose T2. T2 actually say T2. Then T2 it hits where? Go up there. Hits. This is the point. This is the point on the curve, APPO curve. That should be satisfied. So first hit that. T2 curve. This point on the APPO. This point must be this. Through this point, the carbon curve must also pass. So carbon curve must also pass through this point. Repeat. T2. Sorry. T2. Sorry. T2 go up. Here, this point, which curve? Now, this curve. Which curve? 1 atmosphere total pressure. Passes through this point. Automatically, it must be 1 atmosphere. It cannot be otherwise. You cannot change it. Inflexible, 1. No, not even slightly changed. Just 1. Means no freedom. So that is dependently fixed. That is no sign of freedom. So similarly T3 go up. Which point hit? This one. This point of a PPO curve, and through the which correspond to which pressure of total pressure CO2 curve, carbon curve passes through this. Now 5 atmosphere. So P is 5. Similarly, P is 10. Okay, here. Now, conversely, you see, since I started with T, conversely, since degree of freedom is a matter of choice, so you fixed pressure. Pressure you fixed, not temperature. Pressure. Then pressure fixed. Say again, consider. Then you have to show 1 degree of freedom. Say apply. Say any of them. Suppose 1 atmosphere. Also 5 atmosphere. This line this curve you chose freely. 5 you are choosing, not 1, not 0.5. Means free. Arbitrariness. So 5 atmosphere. This is this curve. Choose where it hits. Okay, meets APO curve right here. That is the meeting place where actually these are all coexisting meeting place. Coexisting. What temperature it corresponds to? Come down on the x-axis scale, reads T3. So T3 is the dependently fixed. Is the temperature automatically fixed, dependently fixed. This is the message. So this let us write it out. Okay. Another thing I tell you, since 1 atmosphere is very typical. Just for your information, this is the second curve is for 1 atmosphere. You know, this point, it hits this point. Sorry. This point is actually T2. Corresponds to T2, and the composition is here. This composition, this T2 is, this temperature is actually, I tell you, is well known. Since it is 1 atmosphere, it is well known, 966. T2 is 966. This I'll mention. 966, and the corresponding percentage of this is 63%. Okay. This is what actually. So is what actually I tell you what 59, 63 is this. Okay. 59. Okay. I'm sorry, not 63. 63 is very good. 59. So this, what is this? This percentage. His APO curve here is 59%. This I mentioned. Okay. So T2. Then that's for particularly for 1 atmosphere curve, the values are known. That's why T2 is what and corresponding percentage is what. So that let us write down few lines. If we arbitrarily fix, apply. So remember, these curves are already taught. Example 2, this curve, APO curve, and CO2 see CO curve just few moments ago, example 3. This is 3, this is 2, so it is not right. If we arbitrarily fix T as T1, then what does it mean? The only T1, the only DOF, the only degrees of freedom available the total pressure P of the system is automatically fixed at what? Fixed as 0.5 atmosphere. As 0.5 atmosphere. The first one is this is corresponding to, this is the 0.5 atmosphere curve. So pressure is 0.5 atmosphere. So this is for the equilibrium coexistence of AP solid, APO solid, carbon solid with the gas phase. CO2 with the gas phase at point coexistence where? At point let us give a name to this. I forgot to give name. This is A, this is B, this is C, and this is D. A, B, C, D. This point is A, B, C, D. At point A, point means state. This is the state of the system at equilibrium. Point A, state A. State given by point A. State given by point A. State given by point A. And obviously, of course, the pressure is 0.5. That again depends upon the temperature. Temperature is T1 temperature. Okay. Point of state A. Similarly, if we fix T as T2, the corresponding P is what? 100 square. Note here, since it's a P is 100 square case, so I am giving you the data. Okay. For all pressures, actually all other pressures you should calculate, but this is so frequently used that we know the data. For P is 1, what is the T2? So that is actually well known. This is well known data. The value of T2 is well known as what? 966 Kelvin. Nine 66 Kelvin and percentage corresponding and percentage CO here at this point B here how much it is, as I told you, 59%, and percentage CO is and percentage CO is 59, like this. So B is 59 here, and T2 is 966. T2 is 966. Okay, anyway, don't worry. This is additional information. This is additional information. Okay, this is T as T3. Similarly, continue. If we fix T as T2, T as T3, the corresponding P is right here, point B. Add here point B. Point B. Because here point A I have said, point B, T as T3, the corresponding P is 5 atmosphere, point C. Point C. And here you see, well, if we fix T as T2, the corresponding P is 1 atmosphere, and similarly continue. Fix T as T3, the corresponding P is 5 atmosphere, and finally T as T4, T as T3, it should be a comma here. T2, there is a comma here, okay? The corresponding P is what value? 10 atmosphere. See here, it is written here 10. Last one is 10. 0.5, 1, 5, 10. 0.5 A, B, C, D. Temperature T1, T2, T3, T4. And percentage will be actually, just you have to find out, you have to read off the scale. Actually for B at least we know the value is 59%. Okay. Accordingly this can be found. Okay. And the P is the corresponding P is 10 atmosphere, so point D. Point D means state D or point D or state D. Point D. Conversely, now as I told you, conversely, okay, why give a star here and write where you write a demonstration. This is not so important anymore. Let us have some space here. These two lines, remove these two lines. P. Conversely, star. Conversely, what I say conversely, fix P and see T is automatically. For example, suppose you choose P as 1 atmosphere. What is the automatic? It is hitting the FAPO curve where at D. D corresponds to temperature T2. T2, which is actually, as I said, 966 Kelvin. Similarly, you choose 5 atmosphere curve, then it hits point C. C corresponds to T3, automatically fixed. So this I am going to explain here. Conversely, and for the sake of what? For the sake of completeness, sake of clarification, if we arbitrarily fix P instead of T at, for example, 5 atmosphere. As, wait a minute. As the only degree of freedom, as the only degree of freedom, 1 degree of freedom, 5 I say, 5 is arbitrary 5, it is not 1, it is not 10, it is not 0.1, 0.5, 5, fix, arbitrarily fixing, so degrees of freedom, 1, I am applying, then what automatically, 5 here I consider, 5, if it is 5, then it is hitting at point C. C corresponds to temperature T3. So it is the only degree of freedom, as the only degree of freedom available. As the only degree of freedom available. One degree of freedom available. Then T will be automatically fixed as what? You cannot say any other value, as must be T3 as T3 and the state of the system, remove this, and the state of the equilibrium coexistence of Ap solid, APO solid, carbon solid, CO gas, CO2 gas will be given by, this state will be given by which point? Since 5 hits point C given by, and which corresponds to temperature T3. T3 we have said automatically fixed, will be given by point C. Point C. Point C. This is in figure 5, as you see, figure 5. With this, we have completed example 5 and this figure also, including this figure. So next we will take up 6. What we will do? From now I am telling you. Here it is already there. We will introduce another one, another solid, relevant solid. What is this? Fe3C, carbide, which is cement type, Fe3C. That will, and see how it modifies the degrees of freedom. Number of components, number of independent reactions, etc., etc., and degree. Finally, most importantly, degrees of freedom. And then we'll demonstrate how by fixing, if it is available, the degrees of freedom, we can define the state of the system at equilibrium. So this is very interesting and very, very important also. So let us move on. And it's better actually now, where it is, we should remove this. Everything we should remove. So figure 5b, I am removing this figure, no longer required. Is okay. So start. So which one? This is actually example Acha, this is figure 6p. So this fencing should be there. 6c. This is okay, and this is also should be kept intact. This is the figure 6 B C D. Remove this. Okay, this is very good, looks fine. So 12 examples we'll take. This is the sixth. Sixth is what? As I told you, keep on right. Again, I am giving this equilibrium, which you will make a phase rule analysis. Of which you will make a phase rule analysis. Fe solid, FeO solid, carbon solid. Now additional Fe3 solid. Fe3 is the new entry. Okay, CO gas and CO2 gas. This is your system. Okay, so you draw this as usual. Now take a look if it is okay. Position is okay.
Okay.
Okay. Huh?
Okay.
Okay. How many minutes left? 10 minutes or 12?
No, 13.
This is your P. This is your P. The phases you can write Fe. Is there too many? Okay, it is better. It is Fe solid. You want to write Fe solid. Fe solid. FeO solid. Carbon solid. Fe3 C solid, and you have a gas CO2 gas. Is under equilibrium. This is your figure 6a, and the subsequent figures are 6b, 6c, 6c. This will be used. Okay, so we start our traditional way. What is this? Write the degrees phase rule, Gibbs phase rule. F is C minus P plus 2. We will make a phase rule analysis. Okay. First we will find out the degrees of freedom. Rather, we will first find out C, number of components, then number of phases, and then degrees of freedom. And then we will demonstrate how by using F, okay, variables. F variables given by the degrees of freedom. F variables. The state of the system can be described at equilibrium. That is temperature, pressure, and composition of each phase at equilibrium. So this is the given thing. C is, you start again. C is what? Again, I should say number of elements. Go by this. Since the reactions are not given, you have to find out the reactions yourselves. Then you go take that trick, take that path. Find C from the number of elements and use that back into the other definition of C, which involves number of independent reactions. Number of elements. Obviously, this is sorry. Number of elements is nothing but 3. Who are there? Fe, carbon, oxygen. These three elements is what? Number of species minus number of independent reaction equilibrium, number of independent reaction equilibrium, number of species is very easy to find out, is what it is. As I am writing underneath, this is how many species? 1, 2, 3, 4, 5, 6. 6 is who are there? 6 is AP, APO, C, AP3C, CO, CO2. 6 species. So, or number of independent reaction equilibria is what? 6. And it is what? How many? 6 minus 3 is 3. Which are they? You just keep writing. The possible, which you choose actually. Number is 3. What is this? APO solid plus C involving any 2, 3, 4, 5, 6, 7, 8, any, okay, as far as possible available. Okay, so APO, what I am choosing? APO, CO, AP, CO2, like this. APO, CO, AP, CO2. This whole thing is in equilibrium. All possible reactions are under equilibrium. By chemical equilibrium, this I said before, that all possible reactions are under equilibrium. So I am choosing this. APO solid plus CO gas goes to AP solid plus CO2 gas. Call it what? Reaction 1. Then next is what? CO2 gas plus carbon solid is 2 CO gas. That is reaction 2. And third would be what? Involving AP3C is yet not involved. That is you have to involve. So 3 AP solid plus 2 CO gas goes to AP3C solid plus CO2 gas. Third. See, this is, see another thing again here. See,
7 minutes.
okay. 3 AP plus C. See, third, 3 I have chosen. You could have chosen 3 AP plus C is AP3C. Like this, okay? So also you can actually, this is possible, okay? You want to, this is fine anyway. Okay. So this I am not, these 3, okay? Don't worry about this, okay? Unnecessarily don't embroil yourself into this complexity or unnecessary complexity. Okay, anyway, you understood. 3 you can choose freely, no compulsion. Okay, at least you should verify that. Okay, so 3. Very good. Then what? Let's start from here. How many degrees of freedom? 3 component is how many? 3. Phase is how many? Oh, sorry. P is not S. How many phases? See, 1, 2. Oh, I'm very sorry. Yes, correct. 1 solid, 2 solid, 3 solids, 4 solids, and 1 gas. So 5. 4 solids. You should mention which are there. AP, APO, carbon, AP3C. 4 solids and 1 gas. So 5. So apply here 3 minus 5 plus 2. 0. No freedom. Very special case. Extraordinary case. So this is 0 degrees of freedom. This is called invariant system. invariant equilibrium, invariant system. System with 1 degree of freedom, system with 2 degrees of freedom, system with 3 degrees of freedom, system with 0 degrees of freedom, invariant system. Okay, this we have come across. Okay, so I told you once that triple point, a single component like say water, the triple point is a invariant equilibrium, but no freedom, all are automatically chosen. So this you have to demonstrate. This is it's a demonstration. Now demonstration. Remember, you cannot fix. Previously, we started how? By fixing temperature. But you cannot write. You cannot write anymore. Because no choice. You cannot fix. But still, you will see they are automatically fixed. Temperature, pressure, and composition, that is the state of the system at equilibrium, will be automatically decided. Let us see how. Demonstration. Okay, delta G02, start with this. Start with me. Delta G0 demonstration. Delta G02 is what? A plus BT. You know, A plus BT form available. A is, known. Delta H0 part is known. B is minus delta H0 is known. There should be available data in this form A plus BT. You have solved many problems with the data, given data A plus BT known is minus R3 ln K, which 2 second K2. Okay, what is this? Keep on writing. Is what? Minus R3 ln K2 is what? K2. Okay, K2 is what? Equilibrium constant. Second is PCO square by PCO2, activity of carbon. At equilibrium always you can attach activity of carbon is 1. So this is one equation is obtained. One, call it equation 1 or what you will call it. Okay, or keep on or continue work here, or PCO square ln PCO square by PCO2. This is ln is what? A plus BT by R3 minus all it equation 4, and we will take up the third one, delta G03. Three is what? Again, it cannot be A anymore, same data, cannot be A prime plus B prime T is what? Minus R3 ln. Similarly, K third 3 is what, right? Minus R3 ln, right here, activity of AP3C solid times PCO2. AP3C times PCO2, activity of AP cubed over PCO at equilibrium, PCO square, PCO square at equilibrium. Again, this is solid, pure solid once, okay, or right, similarly, ln PCO2 over PCO square is nothing but minus a prime plus b prime t by rt or ln PCO square, inverse this, okay, or negative, take negative of this, a prime plus b prime t by rt is okay, this is okay, minus is absorbed, okay, is PCO2 by PCO square, okay, minus a plus bt is okay. So call this 5. So from 4 and 5 you see left hand side same. So from equation 4 and 5, equations 4 and 5, what you are getting, a plus, right, minus a plus bt a prime a plus bt minus, okay, by rt is a prime plus b prime t by rt. rt cancel, or what you are getting, a prime plus a is minus b plus b prime t, or t is what, minus a plus a prime over b plus b prime. Let me check, it is minus a plus a prime b plus b. Since a and a b a prime b prime, right here also, right here, known quantities, so all are known, so temperature is automatically known. So you write here this
2 hours, 2 minutes.
automatic, 2 hours,
2 minutes.
okay, automatically fixed. Okay, automatically fixed, this is okay, automatically fixed, about 2 minutes more, automatically fixed, okay, automatically fixed, okay, this is very good. So temperature is automatically fixed. So let us see pressure now, pressure composition, etc. So pressure, once T is known, once T is known, automatically fixed. So anyhow, it is found, dependently found. Once found, T is known, what you know, you write here, okay. KT1 is what? KT1, first one. KT1, first one. See, recall this one. Activity of Fe solid times PCO2 over activity of FeO solid times PCO at equilibrium, as you write. This is 1, this is also 1. So equation, this, shall I give a name to this? 6 perhaps. 4, 5, 6. 6 and KT2. Similarly, KT2, second one is what? PCO square by PCO2, activity carbon. This one, second one, PCO square by PCO2, equilibrium. This is 1, activity carbon. So call it 7. 2, so KT, since T is known, so KT is known. So solving, so let us, so I am actually, let us write this down. Solving equations 6 and 7. 6 and 7. gives what? PCO out, PCO2, two unknown, two equations, PCO, two unknown and two equations. So PCO out, and this leads to P is what? Total pressure is PCO plus PCO2 is also known. So composition is what? So this. So XCO is what? Keep on, right? Composition XCO is what? PCO over, right, this way. PCO over P is known. Similarly, XCO2, which is PCO2 over total pressure, P is known. Composition mole fraction is known. What else? And about the solids, pure solid, pure AP solid leads to XAP is 1, pure APO solid leads to XAPO is 1 mole fraction, pure carbon solid leads to XC is 1, and pure AP3 solid leads to X AP3C is 1. So all solids. So composition of all four solids and gas phase, so all over. So you write here, hence star here this side. The last line. So very interesting. So without independently fixing anything, since F is 0, the system is defined. State of the system at equilibrium is defined in terms of temperature, pressure, and composition of each phase. So what's that? Right? Star. I should give star where? It will be here. Good enough here. Okay. So without 1 minute, 1 to 2 minutes, without independently fixing, this is very special case, without independently fixing any variable, so invariant system, the system is fully defined in terms of temperature, pressure, and composition. Of each phase at equilibrium. At equilibrium, all variables Bapu, Take a look if it is seeable here.
It's visible.
Visible, so automatically fixed. Last line. All being automatically underline. Automatically means without dependently. So without any degrees of freedom, all variables automatically fixed means dependently fixed or automatically fixed. Okay, without any freedom of choice, automatically fixed. Last line is okay. Automatically fixed. Thank you very much for your thank you for your interest and your cooperation and your patience and for your sincerity. Thank you very much. So today this is not yet over complete. Okay, 50% or 40% over. Remaining 60% is what? This curve, these three curves. That is a stability diagram. So about stability diagram, this requires discussion. Okay, some discussion. So that will be taken up next class. So today we will actually call it a day. So thank you very much. Bye.